Hello and welcome to this video. Today I'll be talking about three topics: computer architecture, organization, and finally scheduling algorithms. Computer system architecture is the design of a system that defines the method in which a program's logic is executed. Hence, we can say that computer architecture refers to those attributes that have a direct impact on the logical execution of a program. In other words, it is a set of rules and methods that describe the functionality of a system. It is important to note that computer architecture mainly deals with how hardware components are connected to each other, and that is important because it serves as a bridge between hardware and software, because it shows how software would exist in the framework of the computer system. So, say you have a program to execute, what will the computer architecture define? It will define how the instructions and the data will travel from one component to another, from the memory to the control unit to the arithmetic and logic unit. It will connect them. It will show how these components are connected through the flow of information and instructions. That is really the architecture's domain. And the computer architecture will also include the instruction set, which is the complete set of all instructions in machine code that can be recognized by a processor. So that is of course very important, and the differences in the instruction sets can determine the functioning of the program, whether it functions fast, whether it functions efficiently, or whether it functions badly, poorly. All that can be determined by the instruction set, which I'll come to in the examples to come. And examples of instructions are the arithmetic and logic instructions, the memory allocation and memory retrieval instructions, input-output instructions. And the computer architecture also includes the definition of the number of bits used to represent various data types, for example, integers or characters or float data types. And it also includes the techniques for addressing memory. And I will come to that in a while. So, a computer system architecture defines what a computer does, what is available for the computer to use. On the other hand, the computer system organization defines how a computer does what it's supposed to do, how a computer realizes its architectural specifications. So to give you an example of the difference, it is an architectural issue whether a computer will have a multiply instruction, but it is an organizational issue whether the instruction will be implemented by a special multiply unit or by a mechanism that makes repeated use of the add unit of the system. So by definition, the computer organization refers to the operational units of computer, such as the processor and the input-output devices, and the interconnections that realize the architectural specifications. So in other words, the details that go into the physical realization of the architecture is the domain of organization. What technology to use, what algorithms to implement to achieve certain requirements that are stated by the architecture. All that is in the domain of the organization. And yes, briefly touching upon the memory addressing techniques that I was talking about before, they're really addressing modes. So you can check on that. So it really refers to the way in which the operand of an instruction is specified, or in other words, if an instruction requires a data, how is it retrieved? So that is the domain of memory addressing techniques. So while these might be defined in the architecture, of course, the way they're implemented is the domain of organization as well. Now we go on to examples of different architectures. Now moving on to examples. So the first one is the von Neumann architecture, which was published by John von Neumann in 1945. His computer architecture design consists of a control unit, an arithmetic and logic unit, memory unit, registers, and input-output. Now this is very familiar because it is still very widely used today. And the reason why is because this architecture is based on the concept that instructions and data are stored in the same memory. This design makes computers easier to reprogram since instructions can be accessed from the memory, they can be changed, and new instructions can be made and put back into the memory from where the computer can read and execute these instructions. This design, of course, because of this programmability, is still used in most computers today. So I spoke of the advantage of the von Neumann architecture, which is the programmability of the instructions. But now I'll be speaking of the disadvantage, which mainly is that the instructions and data have to compete for the same buses. So there may be inefficiency due to that. And this is what the Harvard architecture addresses. So we move on now to the Harvard architecture. So the Harvard architecture is an architecture wherein there is separate storage and separate pathways for the instructions and data. And by pathways, of course, I mean buses. And this contrasts with the von Neumann architecture, where the instructions and data have to share the same memory and the same pathways. This increases the efficiency of the CPU because the data and instructions do not have to compete for the same buses. However, their disadvantages are that there is higher hardware complexity because of the dedicated storage and the dedicated pathways, and there is more usage of power because there is more to power, because there are more components involved, and there is cost because again there is higher hardware complexity, which is usually costlier, and there is more utilization of power. So it's important to note that in Harvard architecture, because the data and instructions are stored in separate dedicated storages, there's no need to make the memories share the characteristics. For example, there's no need to have the same memory address structure. So that it can be different. It can be accessed differently. And this is where we come on to the next point, which is the modified Harvard architecture. The modified Harvard architecture is a variation of the Harvard architecture. But unlike the pure form, it allows the instructions to be accessed as data. And most computers today, which are classified as Harvard architecture based, are in fact modified Harvard architecture based, because it is more practical in terms of the cost and in terms of the hardware complexity. But of course, the modified Harvard architecture has separate buses for the instructions and for the data, because there has to be some element of the Harvard architecture for it to be retaining some of the name, right? So it has some part of von Neumann's architecture, but it still retains the aspect of separate pathways for the instructions and data, and it may have separate caches for the instructions and for the data. So it is in a way the best of both worlds, because it allows for quicker performance, for more efficient performance than von Neumann, because data and instructions can be processed at the same time. However, it mitigates some of the disadvantages of the Harvard architecture, such as the hardware complexity and the power and the overall cost. Now we move on to architectures that differ in terms of the instruction set. Now if you remember what instruction sets are, they are the complete set of all instructions. They are low-level instructions. They are in machine code. So they are the complete set of all instructions that can be recognized and executed by the processor. These are the instructions in a processor from which every other instruction is built. And of course, the mapping from the higher level instructions to the lower level instructions is done differently depending on the instruction set. The first one is the reduced instruction set computing architecture. So in this one, the aim is to make instructions as simple as possible and reduce the hardware complexity to the maximum. The other one is the complex instruction set computing. Here, while hardware complexity is increased, what it aims to do is reduce the number of instructions required to do a certain higher level instruction, for example. So, for instance, in an RISC architecture, if I give a higher level instruction, it will translate to many simple instructions. But in a CISC architecture, the same instruction will be translated to fewer number of instructions, but they will be more complex. So why these differing techniques? This is because a processor's performance can be increased either by making the amount of time required to execute each instruction smaller, or by making the number of instructions lesser. So the RISC focuses on the first one, while the CISC focuses on the second one. Now moving on to the next topic, which is scheduling algorithms. First, let's understand what's CPU scheduling. Now, CPU scheduling is a process which allows one process to use the CPU while the execution of another process is on hold. Why would the execution of another process be on hold? It could be because that process is waiting for the input, or it could be because it needs another process to finish before it can move on. So, as I said, CPU scheduling is a process, and as any process, it is backed by an algorithm. Such an algorithm, of course, is a scheduling algorithm. These algorithms decide which process to execute among a set of processes that are in ready state or in waiting state. Ready state means they can be executed but they have not been executed yet, and waiting state means they have been executed but are temporarily put on hold. So, what these algorithms do is help in maximizing the CPU utilization by executing the processes more effectively and more efficiently. I will now be discussing the different algorithms that are available for the scheduling process. The simplest algorithm is the first come, first serve algorithm. And this just involves one first in, first out queue. So the process which requests the CPU first is allocated to the CPU first. So when a process enters the queue, it is linked at the tail of the queue, and when the CPU is free, the processing time is given to the process at the head of the queue, and that process is taken out from the queue, of course. The main advantage of this algorithm is that it's very simple to implement, but the main disadvantages are long waiting times, especially if the first process takes too long. Also, the priority of the jobs are not considered. Also, it doesn't consider the time durations of the processes. So, a process that needs a resource for a short amount of time is not given that resource, while a process that's holding the resource for a long amount of time keeps holding it and prevents all the other processes from using it, even though it would be optimal for those processes to use it first and then this process, because this takes too much time. So all that is ignored in this first come first serve algorithm, and this is where we move on to the other algorithms, such as this remaining time first algorithm, where processes that take less time to execute are given the processing time first. Before moving on, I'd like to define a few terms. Starvation. Starvation is a situation where a low priority program is not able to access a resource because high priority programs use that resource for an extended amount of time. And in this case, you can imagine the situation where smaller processes keep coming in while a longer process is put on hold for an extended amount of time because it's not able to use the processing time. And this is the problem with the shortest remaining time first algorithm, as well as the next algorithm, which is the priority based algorithm, which is the algorithm wherein processes are scheduled according to their priorities. And how are priorities defined? There are various ways to define them. In some ways, the shortest remaining time first algorithm is also a priority based algorithm because the priority is defined as the shortest process is given the highest priority. But of course, this extends beyond that, and processes can be defined as having high priority either by default, or you can also define high priority processes. An example of a low priority process is backup, routine backup, I would say. And with this scheduling algorithm, if there's a routine backup going on and there's an input which initiates another process, since backup is less important than any other process that a user runs, that process will be given the processing time first, and then processing time will be given back to the backup once the process has been completed. Here again, the situation of starvation can occur when a low priority process is put on hold for an extended amount of time because it's not able to access the resource that is being used by high priority tasks that keep coming in. Next comes the round robin scheduling. This is interesting because here the queue of ready processes is treated as a circular queue. So each process in the queue is given a fixed amount of time called as a time quantum or a time slice. Essentially, the processing time is divided into very small slices, and each slice is given to each process in the queue. The queue can be a first in first out queue itself, and the new process can be added at the tail, and the oldest process will be at the head of the queue. And once the oldest process has been finished, it will be released from the queue. So this is the round robin scheduling, and this is actually a very interesting method because it simulates multitasking. And finally, I'll discuss two other algorithms, and although there are other algorithms as well, These are the two algorithms that I'll finish with. One is the multi-level queue scheduling and another is the multi-level feedback queue scheduling. Now, the multi-level queue scheduling is just an extension of the other algorithms. So instead of having one queue, there are several, and the queues are based on priority. So there's a top level queue with top priority tasks, and then there is a bottom level queue with the lowest level of priority. So the queue at the highest priority will be executed first, and only then will the scheduling of the next queue start. Next, we move on to multi-level feedback queue scheduling. It allows processes to move between queues. So if a process is taking too long, for instance, it can be moved to a lower priority queue and the other processes can carry on. So multi-level queue scheduling will suffer from starvation time to time. However, multi-level feedback queue scheduling will suffer less, because although there is a priority in queues, a task can move between queues, which means that a high priority task which takes too long can be moved to another queue, and lower priority tasks which take less time can be executed first. So although there is still chance of starvation, and of course there will be starvation here as well, it will be reduced because of this mechanism. So that is it for this video. Thank you for watching. It was an overview, a brief overview of each topic and each subtopic in each topic, but hopefully it was helpful. Thank you again for watching. Goodbye.